You're probably familiar with Newton's cradle. Although Newton's cradle usually has 5 spheres swinging back and forth, what Newton used actually only had 2 spheres swinging back and forth. And Newton's laws only apply to hard bodies or point masses. Leibniz asked a very good question, well, what would happen if we had larger objects? And what if those objects were not only hard, but what if they were soft? And some very strange things would happen when we introduced soft bodies. Here we can see that if we were to drop a soft body, the soft body sticks because it deforms, it is plastic. Whereas if we drop a hard body, the hard body bounces. It is elastic. Galileo noticed a relationship between the distance fallen and the square of the speed. Galileo raised this idea of a quantity of v squared. Leibniz investigated it with these colliding bodies, and it was Wallace, Wren, and Huygens who explored it and came up with papers based on the collisions of hard bodies and soft bodies. Here we can see a picture of where Newton examined colliding bodies of different masses. And the question was raised, what happens? What is conserved? Do we have just momentum conserved or some other quantity? That other quantity was known as vis viva. This vis viva seemed to disappear when soft bodies would collide, such as an inelastic collision as we see here. However, when we had the collisions of hard bodies, this vis viva or v squared term would not disappear. Vis viva was conserved in elastic collisions. Vis viva, mv squared, can be conserved, and we can come up with equations that dictate the conservation of this vis viva. m1v1 original squared plus m2v2 original squared is equal to m1v1 final squared plus m2v2 final squared. This looks like our law of conservation of momentum, but it is something else. For hundreds of years, this theory persists, but Newton never believed it, and the followers of Newton did it, and hundreds of years later it developed into what we now call the theory of kinetic energy. Engineers in particular liked vis viva because they could use vis viva to explain how much momentum would be transferred in a collision. So by combining the ideas of vis viva with the law of conservation of momentum, we can predict just how much momentum would be transferred in a collision. You can't get more momentum out than you put in, and you can't get more vis viva out than you put in a collision such as this.